object here. Think of it as a metal block if you want. There's a certain amount of energy that flows in and a certain amount of energy that flows out. They're not necessarily equal. If it's in thermal equilibrium, they would be equal, but if it's not in thermal equilibrium, then there's going to be some change in energy. So if I start out with, let's say, 100 joules of energy, and I pump 15 joules into it, and I lose 10 joules, what is my change in energy? Or how much energy do I have then? If I start with 100, I pump 15 in, and I take 10 out. What do I have now?
105. Oh.
If you have $100 and somebody gives you 15, but you spend 10.
I thought.
So my change in energy is equal to 5 joules, which is basically my energy in minus the energy out. Now, energy in, of course, we can't just call it energy in. We've got to call it something else. We call that heat, symbolized by the letter Q. Energy out, well, how do you get rid of energy? How do you expend energy? Well, you expend energy by doing work. So this is work. So the change in energy is equal to the heat minus the heat, which is energy transferred into something, minus the work done by the object. And so we can rewrite that as the heat is equal to the change in energy plus the work done. Now, all I've basically done is taken a look at energy. We start out with a certain amount, we gain some, we lose some, we write an equation, and then I just changed 2 of the letters. From someone who's studied high energy physics, this is my feeling of what they do in thermodynamics. They take the stuff that you've been doing all along, or the ideas, basic concept of energy conservation, and they change the letters. But then they make it more complicated, because there's 2 basic conventions. I'm not going to go into the great detail in the 2 basic conventions, but I can look at this 2 different ways. I can look at it from the object's point of view. I start with 100 joules, I add 15, I use 10, I now have 105. Or you can look at it from everything else's point of view, not the object, but everything around the object, which lost 15 joules, gained 10 more, and so it had a change in energy of -5. If this gained 5, then everything else lost 5. So the first chapter in thermodynamics textbooks is to tell you which one they're doing. Do they look at it from the point of the small object's point of view or from the environment's point of view? It's all conservation of energy. Where I really wanted to get with all this, that's just sort of some background. We have this change in energy of an object. Well, if I have a change, what are the 2 types of energy we're talking about here?
I have mv squared.
Okay, which is? Yes. Sort of backwards from what we usually do. So that means I have a change in kinetic energy, or what's the other one? Yes. There's a change in potential energy. So one of those 2 things is going to happen. So I have a change in energy here, so I have a change in kinetic or a change in potential energy. Now my change in kinetic energy, sort of 2 things can happen here. We can look at it from, there's a change in kinetic energy on a large scale, which I'm just going to call it delta K macro. Here's an example of a change in kinetic energy on the macro scale. It's sped up. Thermodynamics generally doesn't deal with that, so I'll just sort of underline that as sort of a dead end in thermodynamics. The other thing that can happen is a change in kinetic energy on the micro scale. So delta K micro. In other words, the atoms start speeding up just a little bit. And thermodynamics does deal with this. Now, if I start making the atoms start to move faster or slower, depends upon if I gain kinetic energy or lose kinetic energy. The 2 big things that could happen are there's a change in the temperature of the object and or a change in the length. If I add kinetic energy into the particles, in other words, I make them get hotter, it does get a higher temperature, and it starts to expand for almost everything. There are some exceptions. If I have a change in potential energy in thermodynamics, I have a change in the phase. So liquid to gas, gas to liquid, liquid to solid, solid to liquid, gas to liquid, or gas to solid, solid to gas. And so we'll take a look at each of these things separately. Side note here, this equation right here, this is known as the first law of thermodynamics. It's a fancy and far more complicated way of just expressing energy is conserved. We'll eventually talk about the second law of thermodynamics, which is the depressing one. It's more downbeat than the third law. And then there's also a 0th law because they didn't want to renumber it once they realized, hey, wait a second, we have something more fundamental. The 0th law of thermodynamics explains what do thermometers really measure? It's not the temperature of the air. Same way that scales really don't measure weight, scales measure normal force.